Okay, let's solve this particular problem. It's called copy list with a random pointer, and it's from LeetCode 138. So let's read the problem, what it's saying. It's a linked list of length n is given such that each node contains an additional random pointer, which could point to any node in the list or null. So there's an example right below. Uh, and essentially a linked list, each one has a next pointer pointing to the next object, and the last node doesn't have any next pointer, any other nodes left, so it points to null. And each node can have another pointer called random, and random can actually point to any other nodes in the linked list, or it can also point to null. So essentially, it's a graph basically. So what is it asking? It's asking us to construct a deep copy of the list. The deep copy should consist of exactly n brand new nodes. Essentially, what it's saying that for every node here, if you look on the screen on the right side, uh, if we have a node 7, then it's asking us, so this node, existing node 7. So it is asking us to create a corresponding new node. Let's show it in a different color, red. So it's a new node 7. Now, similarly, if we had a node uh, called 13, sorry, this is not the right color. Um, so if we had 13 as the next node, we should have a corresponding node which has is a new one. So then if 7 and 13 were connected, let's say 7 had this um, relationship like this is the next one, and the random is just null. And in that case, it should actually have the same structure. And 13, this node has null, is a null, and all that. And essentially, we will need to return this first node of the newly created linked list. So that's basically the objective. Let's read through. Construct a deep copy of the list. The deep copy should consist of exactly n brand new nodes, where each new node has its value set to the value of its corresponding original node. So that means if you had 7 here, you have a 7 here, you had 13 in the next node, you should have 13. And this 7, 13, this is one in red. This is the new link that they return. And they should have similar structure. Both the next and the random pointer of the new nodes should point to a new nodes in the copied list such that the pointers in the original list and copied list represent the same list state. That means if you had this 7 and you had previous, this on the left is the original one, the 7, the 13 is a clone, and this 7 has to point to the 13, this new node in the clone. They cannot actually just the new clone cannot point to any node from the original linked list. And for example, if there is two nodes, x and y in the original list, where x at random points to y, then the corresponding two nodes, x and y, in the copied list, x random should point to small y. So there's x small x should point to small y. So that's how it should look. And we have to return the head of the copied linked list. So that's what I was saying. We need to return 7 if there's a sequence of nodes here. And the linked list is they're represented in the input output as a list of n nodes. Each node is represented as a pair of value and a random index. So values are 7, 13, these are the numbers. So in this example, you see 7 and null. So 7 is the value of this node, and null is what it is pointing um, in the random order. So it's random, it's not pointing to anything, it's null. And next, 7, this node points to 13, and then this 13 node has a value 13, and it is pointing to node called 0. So 0 is basically the first one is the 7. And then 13, this is the next node, third node is 11. So this node has a value 11, and its random pointer is pointing to 4, so 0, 1, 2, 3, 4. So this node's random is basically pointing to this node called 1, which is the 0, 1, 2, 3, 4. So is it that that node here? So that's what we have to return, and we have to think about a few cases here. This is a linked list, so if we have to copy, we basically have to go through all these nodes at least once. So there can be n number of nodes, and n number of nodes can have n number of random pointers. So essentially, if we want to um, clone this, we will have to clone essentially everything at least once. So the runtime complexity for this one would be the time complexity will be order of number of nodes and plus order of number of random pointers, right? So if you sum them, this is again order of n. So and for space complexity, um, the additional space we need to store the new nodes is not considered, but if you want to just keep all these nodes in the memory, you will uh, need extra space for that. And um, for each new node that we are creating in the clone, if we want to just set their random pointers, we will have to have some kind of a mapping between this previous 7 and new 7, previous original 13 node and the new original clone 13. So we're going to need um, we're going to need a hash map here. So this is the time complexity. So time complexity order of n, and space complexity is also order of n. And now let's get rid of these drawings. So how are we going to approach this problem? So essentially, we will need to have one step we will go to create the mappings between these nodes. So essentially what we're going to do is if we have node 7, we're going to create a new node 7. And in our map, we're going to remember, okay, this is the connection. And in the next one is 13. We'll just keep a head, and a dummy. D is for dummy, H is for header, and this dummy is gonna stay there, the pointer, and the head is gonna be next one in age, so it's gonna create a corresponding 13, and then we'll just loop to the next one is 11. It's gonna create a corresponding clone, and a closer on the right side, you see. Um, so this is how we're gonna approach this. So this is the first one, and as soon as we have everything, then we can start wearing them up in the next iteration. So when we're done with moving forward and creating the clones, we can again reset our head here um, using the pointer we saved using the dummy variable. So our head will begin at 7. And now 7 has a next is here and 13. So using that, we will just use that to look up the corresponding node in our hash map. So this 13 corresponds to new node 13, and this was the next pointer for original one, and for the clone 7, we will also set the next pointer to the clone 13. And this way we can progress. So let's approach this problem at this point. We had a pretty good case. We talked about the runtime, and we need to also think about use case or the test cases. And this is a standard test cases. We're going to take this one and go through after we have done implementing. And what if there is this node is totally empty, it's null. Technically, we don't have to do anything, right? So first of all, if the uh, head equals null, in that case, we do not need to do anything. We just return head. That's it. Otherwise, we're gonna create a new node. Let's say this is called a dummy, and dummy is basically going to point to head. And once we have set up this dummy and the head, we're gonna look at if head is not equals to null. So we're gonna keep running to 7, 13, 11, 10, 1 until it reaches null. So until this point, we're gonna take each of the node and create a corresponding. Um, I'm assuming we have a hash map. So let's create the hash map, and in the hash map we're gonna put these values. Uh, this is gonna be the put. What you're gonna put? You're gonna put the head. So this value 7, and you're gonna create a corresponding new node, and it should have the same value. So head dot val. So this is how we're going to create this, and we're going to move our head to next node in the linked list. So after we're done, basically our head will not be here anymore. So uh, we'll move our head to the next one. So we're done with the first node. We created 7, put in our hash map, and now we're going to move our head to this one, 13. So we're going to create a new 13, put a 13, and there's a new corresponding 13, and our node is going to be created. And we also need a hash map. So hash map is going to be a mapping between node, and map equals new. Okay, so this is our hash map, and now it's ready. We can create that, and after that, when we're done, we have to again set our head to dummy. So we are done creating all these nodes, right? Now we have to just wire them up. So while head is not null, so again, we're going to go to 7, 13, 11 until it reaches null. And in that case, what we're going to do is we can, uh, this node is map dot get head. So this way, for 7, we know this is the clone. This is a clone. This is a clone node. Clone is going to be this one. And for this clone has a pointer next, but we haven't defined that yet, right? So this is still absent. We haven't made the connection. We haven't wired them up. So what we're going to do is clone next is going to be basically map.get and whatever next had. And in this case, for the last node, you imagine for one, this is the head and the next is null. And if you are looking up in map, in our hash map, using null as a key, this is just going to return null. So we're going to be safe. It's not going to throw any null pointer exception. And clone hasn't been defined. What is a random pointer, right? So we're going to do that same again. Map get head dot random, and that's basically it. But one thing you have to remember, we have to move our head to the next pointer. And after we're done, we're gonna just wear all of them up. And finally, we have to return. We're gonna return. We remember we had that dummy. It's set to 7. But we have to return this one, this 7, right? We have to return this 7, not the left one. So what you're gonna do is we can create uh, we can take map and we're gonna get dummy. So dummy is all still pointing to head, right? So that way we can actually return the new linked list head that we need. Whoa, it passed all the test cases. So amazing. And let's say if it passes. We submit and boom. Yeah, it passed with 100% runtime. It's order of n and it's order of so 77% users have 77% of users with memory. And if you just look into the other solutions, all of them basically use the hash map. It's like a minor optimization that you can do. And another way of implementing this solution would be using a recursive function. But every time just go through the uh, nodes in the network and try to create, you might actually end up having the same order of n space complexity. So uh, and it's also harder to implement and maintain. Uh, so I would stick with this iterative solution basically. And that is going to be the end of the solution.